Right. So today we're gonna just review quickly energetics, that's enthalpy, that's things like exothermic and endothermic and whatnot. Right now, a few people are still missing in class. So we have a little time to play the game, and I'll show you how to play the game. So you're already scenario on the screen here already. So what you need to do, right? You put on your little goggles there. You have to choose two letters and a color heart. So choose any two letters and one of the hearts. And of course, you're gonna be winning certain money and whatnot. And we're gonna actually be using the money to do things today. All right, so each letter is worth a certain amount of money, right? So you two letters that you choose, write down how much money you got, and then the heart will tell you what to do with the total amount of money you got. So for example, if you chose C and L, for me, that's $5 in total. 3 plus 2 is 5. And if I chose the pink heart, let's see what happens. If you chose the pink heart, you have to multiply the amount of money you got by 0. So in other words, I got no money, right? So the heart will tell you what to do. Also, pay attention. If you get a blue or red access card, take it. It can be very, very useful. Still waiting on about 3 people to come to class, so don't worry, guys. Right? So for those who collected cards, for those who collected a blue card, you have $30 extra. And for those who collected a red card, you get something called a shelter pass. So write down what you got and let's move on. How much people are here? One person is missing, but let's move on. All right. So you have some chance to earn some more money here today if you can get your questions correct today. So all the questions in front of us are based on enthalpy. Everyone read the red bubble, the red circle. What type of reactions produce heat, causing the reaction mixture and its surroundings to get hotter? You have to choose the word, well, one of the words from on top here, or one of the symbols. Red one, worth $1. What type of reactions make the environment hotter? So answers are coming up. Right. For the first one, it's exothermic. So that means for the blue one, what type of reaction causes the environment to get colder? That's the light blue one there, or bluish one. And that one will be endothermic. So that's easy questions, because once you figure out which one is exothermic, it's very easy to figure out which one is endothermic. But the green one is going to give some problems. Remember, in reactions is all about breaking bonds and creating new bonds. I had explained that a few weeks ago. That is what a reaction is about. So for the green one, when you are breaking bonds, energy is what? Is energy absorbed or released? Hence, this can be viewed as endothermic. Right. Now, before I reveal the answer there, let me talk a little bit about that. I know a lot of people might be sending answers, but they might just be what? Guessing, because it's either absorbed or released. So let me explain this in a way that you can relate to. So let me just get a little white off area here. I want you to think of energy as money, right? Let's say that we have 2 people, right? Let's say you have one person here, right? We have Jim and another person here, Jerry, right? Now, let's say Jerry Jim gives Jerry money. He gives him $100, right? So Jim is generous and gives Jerry $100. Now, you ever hear the phrase, when somebody is getting richer, that means somebody else is getting what? Poorer. So if Jim is giving Jerry money, by default, Jerry is getting what? Richer. But obviously, who is getting poorer in this process? It would be Jim. I want you all to think of this scenario as the environment and the actual reactants. There's a reactant, sorry, having some problem spelling there. The reactants are the actual atoms that are involved in the reaction. So it's the same scenario. So if the and I want you to think of money as energy. So if the reactants is giving up energy, in other words, if the environment is gaining energy, then it means the reactants are what? Losing energy. And I want you to view energy as heat. So that means in this scenario, if the environment is getting hotter, then the reactants are getting what? Colder. And of course, if we reverse the scenario, let's say that the reactants were to gain energy, then it means that the environment is losing energy. So that means the environment will be getting what? Colder. And of course, when it comes to rationalizing whether it's exothermic or endothermic, it's the temperature of the environment. So let's look at the blue one here, right? Based on your answers, I think some people are guessing. When you are breaking bonds, right? Something is missing here. Hence, this can be viewed as what? Endothermic. In endothermic, right? The environment gets what? Colder. We know this, right? In endothermic, the environment gets colder. So if the environment is getting colder, then the reactants are getting what? More energy. So that means what will happen here? Energy is absorbed by the reactants. So to break bonds, the reactants absorb energy. That means the atoms itself basically gain energy. But who is it stealing energy from? The environment. That's why the environment gets what? Colder. Right? Now, if I give you the answer for that one, well, then the answer for the orange one is obviously what? Well, obviously obvious, right? When forming or making new bonds, energy will be what? Released. Now, obviously, if the atoms are releasing energy, there's only one place it can go, into the environment. Hence, the environment gets warmer. Hence, it is what? Exothermic. Right. How about this one here? The white one. Breaking bond in an endothermic reaction. The breaking bonds energy, the energy used to break the bonds, is it more or less than the energy needed to make new bonds in endothermic, based on everything that I just said there? And all of these questions are little one-mark questions around past papers. I think the answer has to be more than, right? It can't be less than, because to break the bonds, it requires more energy than making new bonds. That means to break the bonds, it absorbs plenty energy from the environment. And of course, if it absorbs plenty energy from the environment, the environment will get what? Colder, right? And the next one is this. Exothermic. Breaking bonds is obviously less than making new bonds. All right. Obviously I'm recording the class. The recording of the class will be available. I will not be uploading the slides itself, right? Just the recording of the class where you can see the slides. All right, so that's a little revision based on what we did a few weeks ago. So if you get to take how much money you got there, so if you be honest with yourself, right? For each one that you got correct, grab the amount of money and write it down. All right, write it down. Right, so this question here, is this endothermic or exothermic? Also, quick question, these energy graphs, right, that you have for these energy graphs that they give you to represent exothermic or endothermic, do these energy represent the energy of the actual reactants, or does the graph usually represent the energy of the environment? So my question to you, just to rephrase that, does this graph represent the energy of the actual atoms itself, like the reactants energy, or the environment energy? Which one does it usually depict? Isaiah, correct. Zachary, correct. Surya, correct. Right. It's always the reactants energy. So it's the energy of the actual atoms and whatnot. So based on this graph, right? Remember, not remember, well, which one do you all think this is? The endothermic or exothermic? Think some people are, I think some of you all are guessing here today, guessing. All right. Okay. So let's try to analyze this. The atoms, when you're now putting the reactants to mix, right? Like like you're putting sodium chloride to mix with, let's say, HCl, hydrochloric acid. The atoms started off with less energy. Right? Look how low the energy is. That's the blue line. And then after the reaction, the atoms ended up with more energy. Look at it. The line is higher. Okay? So if the atoms ended up with more energy, where do you think it stole that more energy from? Didn't it steal it from the environment? So if the environment lost energy because energy was stolen from it, won't the environment get colder because the environment has lost energy? When the environment gets colder, what do you call that? An endothermic reaction. Okay? For those who got it wrong, you think you understand it? That's an endothermic graph you're looking at there. Right. Do you all think you all can, in the exam now, right? If they ask you, what does A represent? What does B represent? C and D, without looking back in the notes, you think you could send it on the chat? What does A, B, C, and D represent? Because those simple questions, they're very frequent in the multiple choice, but they also come in the paper too, the written part of the paper. And it's clear in the screen. A is the energy of the reactants. B, activation energy, right? C is the change in enthalpy. And D, energy of products. Now, this question is worth $5, right? Obviously, each one here is $4. And of course, if you reason out it was endothermic, that's your $5th. So write down how much money you got so far. Right. And be honest with yourself, and guys, because at the end of class, we want to say, hey, how much money you have and whatnot. You know, make it fun. Isaiah, you don't want to say it as heat change. You won't get marks for that in the exam. The official name for C is change in enthalpy. Right, let's move on. Right. So we're going to actually do some heat of neutralization calculations again today. And then, of course, we'll officially start the past paper. Now, I just want to explain the how you call it, the definition of the heat of neutralization. Because a lot of people can memorize the definition, but they have no idea what it actually means. So let's read it here. The heat of neutralization, right? So a neutralization reaction is most of the times between an acid and a base. Because when you mix an acid and a base, you get salt and water. The name of that type of reaction is called a neutralization reaction. So the heat of neutralization is the heat change. Remember, heat is a type of energy which occurs when 1 mole of water is produced between a reaction between an acid and an alkali. The key word here is, is 1 mole of water. So let me put this in perspective. Let's say I do not have 1 mole of water. Let's say I have way less water. Let's say I have 0.04 moles of water. That's way less than 1 mole of water. And let's just say in this acid and base reaction, 0.04 moles of water was produced, and the amount of energy associated with this 0.04 moles of water, let's just say it's 46 joules. Is that the heat of neutralization? The answer would be no, because heat of neutralization is the connection between 1 mole of water with the amount of energy. So what is the heat of neutralization? You're going to have to draw a little cross like this. Mole and energy. According to when we did our calculations, we realized 0.04 moles of water produce 46 joules of energy. But I am interested in 1 mole of water. Obviously, 1 mole of water is going to produce more energy. Can you all help me calculate how much energy is that? Cross multiply and solve for x. And tell me what is the heat of neutralization for this particular question that I made up on the spot. So the heat of neutralization is the energy for 1 mole of water. So let's solve for x. So you have 0.04 multiplied by x, that's 0.04x. And then 46 by 1 is just 46. We want to solve for x. This 0.04 is a multiply, throw him across, you get what? A divide. I know I said it over and over, but bear with me, right? Is that we are calculating the energy associated with 1 mole of water. So 46 divided by 0.04, hey, I'm getting the same answer you guys are getting. 1150 joules. That's the heat of neutralization value, right? Because this is the amount of energy associated with 1 mole of water, right? Right. Great. And also, you all know this formula from physics here, right? This formula from physics is energy is equal to mass multiplied by the specific heat capacity of the substance multiplied by the change in temperature. All right. So guys, let's get ready to move on, right? Let's see what the next thing is about. Get started with this question. Now, I'm going to ask you to not look back in your books. I change up the values and whatnot, but let's see if you can do this question. Do it on scrap paper without looking back in your books. Right. So we're mixing two things together. Sodium hydroxide, but that's your base. Remember, this is a neutralization reaction. And the H2SO4 is your acid. Okay? So the thing about it, the two things that we are mixing at the beginning of the question have slightly different temperatures. I mean, don't get me wrong. After everything was mixed up, the final temperature was 44.2. The initial temperature, don't you think we should find the average of those two values? I'm going to write it here. Initial temperature. Well, the better thing to write is the average AVG. I should spell it out in the exam, obviously. To find the average temperature, we add the 26.5 and the 29, and we divide it by 2. That gives you the average. So let me do that. 26.5 plus, that's all right, 26.5 plus 29, make sure and press equal, and then divide by 2. We're getting 27.75 degrees Celsius. Now, that's the average initial temperature. The final temperature was how much? 44.2 degrees Celsius. That's this guy here. So if it started at 27.75 on average and it ended at 44.2, how much is the increase in temperature? And you just have to minus the two values now. Let's do that. 27.75. Let's minus 44.2. I'm getting 16.45 degrees Celsius. Be honest, guys. How much of you all will not be able to claim your $1? In other words, how much of you all truly got it wrong? For those who got the 16.45, grab your $1. All right. The formula that you're supposed to use was the formula 2 slides back, right? Remember this formula, energy is what? Mass, M is for mass, by what? The specific heat capacity of the substance by the change in temperature. This is the same formula from physics, right? So they want us to calculate the amount of energy. Now, you're mixing 50 centimeters cube of sodium hydroxide with 75 centimeters cube of sulfuric acid. Now, here's the thing. You have to make an assumption, and CSEC wants you to make this assumption. Well, first of all, what's the density of water? Well, 1 milliliter of water or 1 centimeter cube of water. What's the mass of 1 centimeter cube of water, of pure water, according to, well, almost any textbook? If you only had 1 centimeter cube of water, how much would it weigh? This is a standard value. It's 1 gram, right? That's the mass of 1 centimeter cube of water. Now, I know it's not pure water we are using. Remember, this sodium hydroxide is a solution. So this sodium hydroxide is dissolved in water, and this H2SO4 is also a solution. An acid is always dissolved in water. And we have 75 centimeters cube. So you have to make the assumption that when you dissolve the sodium hydroxide and you dissolve the H2SO4 into the water, it doesn't change the density of the water by much. So in other words, how much centimeter cube of liquid did we use? We used 50 plus 75. 50 plus 75 is how much? 125. So we make the assumption that that 125 cm cube weighs 125 grams. Everybody okay so far? You have to make the assumption that the solutions basically have the same density as pure water. Obviously, in real life, it will be a little bit heavier. Everyone good so far, right? So what are we putting for the mass? How much grams are we putting for the mass? Just to make sure everyone gets it. 125, correct. And the specific heat capacity of water, well, per gram, they gave you it is 4.2. And how much was the change in temperature? The change in temperature was 16.45. Multiplied out, and that will give you what? The heat, the amount of energy, no, right? The heat change. When I say heat change here, they mean heat energy change, or the change in energy. 125 by 4.2 multiplied by 16.45. Let me know if you guys are getting this. 8636.25 joules. Right, so a lot of people are seeing where they went wrong. Now, I have two assumptions here for part C. I wasn't supposed to show the answer, but it's on the screen already, so I can't do anything. State two assumptions Jimmy made in the previous calculation, but his name was supposed to be Tommy, but I put Jimmy by mistake. Right, and one of them, you know it already. The sodium hydroxide and the H2SO4 have the same density as water. That's the only reason we could say 50 centimeter cube of the solution plus 75 centimeter cube of the other solution when you add them together. Only because of the assumption we can see everything weighs 125 grams. But like I mentioned, in real life, the sodium hydroxide and the H2SO4 will change the density of the mixture a little bit. And also, we are assuming that there are no heat losses in the experiment. Right? Let's move on. This is your job now, guys. Calculate the heat of neutralization. And I've already balanced the equation for you, H2SO4 and whatnot. In the exam, the examiner will not balance the equation for you. You will have to balance it off first and then calculate the heat of neutralization. Good luck. Right. So if you look at the balanced equation, first of all, remember the heat of neutralization has to do with energy and water. Remember, we had cleared up the definition a few slides ago. So we want to know how much energy is associated with exactly 1 mole of water. Now let's look at the ratios. When you are comparing ratios in a balanced equation, you can only do it with moles. You cannot do it with grams and kilograms. It only works with moles. So look at the sodium hydroxide. The big number in front of the sodium hydroxide is 2. And the big number in front of the water, the H2O, just so happens to also be 2. So the ratio of sodium hydroxide to water is 2 to 2. Obviously, if you simplify this, 2 to 2 is the same thing as 1 to 1. So the ratio of sodium hydroxide to water is technically 1 to 1. What does that mean? This ratio represents the moles relationship. A ratio of 1 to 1 means how much ever moles of sodium hydroxide you have, you will have the same exact amount of moles of water. It's like money. If it have two people and I say to share the money in a ratio of 1 to 1, if I give the first person $20, because the ratio is 1 to 1, the other person also has to get what? $20. But the question is now, right? We don't even know, well, right now, we don't even know how much moles of sodium hydroxide was used. It would be so nice if someone told us how much moles of sodium hydroxide we have. But we kind of were given that information. Look up here. They said they gave us 50 centimeters cube of sodium hydroxide solution with a keyword here, concentration of 2M. So let's draw a little cross here. What does 2M mean, right? 2M, capital M, is the same thing as 2 capital M is moles per 1,000 centimeters cube. That is what capital M means, moles per 1,000 centimeters cube. So we have moles and volume. According to the concentration, since it's 2 capital M, that means in 1,000 centimeters cube, we have exactly 2 moles of sodium hydroxide. That is what it means. That's the concentration. But did we use a full 1,000 centimeters cube? No, we only used 50. So in 50 centimeters cube, we are going to have a less amount of moles. By the way, this is for the sodium hydroxide that we're calculating. You think you all can solve for X there for me? I want to know how much moles of sodium hydroxide exist in 50 centimeters cube of the solution, given that you know the concentration. Cross multiply and solve for X. Easy piece of calculation there. Cross multiply here quickly. 1,000 by X is 1,000X. 2 by 50 is 100. Yeah, I think you guys are correct. Throw across the multiply. You're going to get a divide. So X is 0.1 moles. All right. So this is what we know so far. The amount of moles of sodium hydroxide used, 1 second, was 0.1 moles. Quick question. How much moles of water was created? The answer is literally on the screen there. The amount of sodium hydroxide was 0.1 moles. So how much moles of water was created? 0.1. Remember we said the ratio was 1 to 1? So the amount of water created was 0.1 moles also, due to the ratio. But we're not finished. Do you all remember from the previous question how much energy was created in this reaction? Let me write back the value for you. The amount of energy created was 8636.25 joules. I have no doubt you all remember that value from the previous one. So that means when 0.1 mole of water was created, this is the amount of energy associated with it. But heat of neutralization does not care about 0.1 moles of water. Heat of neutralization cares about what? Exactly 1 mole of water, not 0.1. So let's put moles and energy here. For 0.1 mole of water, the amount of energy was 8636.25. So if we have 1 mole of water, which is way more moles, how much energy would be created? That X value there will be your final answer. That will be the heat of neutralization. I think you can do this one in your head because 0.1 is already 1/10 now. So if 1/10 is this amount, remember a whole one is 10 times larger, right? But anyway, send the final answer on the screen, cross multiply, solve for X. You're just basically multiplying this by 10. You're going to get 8636.2 and then the 0.5 joules. This is your heat of neutralization. Right? This is just a revision question. I just changed up the values. That's all I did. Right. Right. This here, by the way, is what type of energy reaction? This is part E to the question, right? What type of graph is this? Exothermic or endothermic? Right, this one is obviously exothermic. And how do I know that, right? I know I've seen it over and over, but I like to always reason it out. Remember, the products is the last line, and the initial stuff that you're putting are called the reactants, right? So if the products, if at the end of the experiment, you end up with less energy, the molecules end up with less energy because it's lower than the blue line. That means it lost energy. Where did it give the lost energy to? It gave the lost energy to the environment. So if the environment gained energy now, then it got hotter. So it has to be what? An exothermic reaction, right? And by the way, neutralization reactions, like when you mix an acid and a base, they are exothermic reactions. They make the environment around it hotter, right? And you all know how to label this already, right? Energy of the reactants, activation energy, change in enthalpy, and products. All right? So grab your $4. If you knew you would have gotten this correct in any case, right? So grab the money, be honest with yourself. All right, so let's move on. Oh, by the way, we have a new thing now. When people are not participating in class or not participating enough, we have special punishments. You all can read the various punishments, and we're going to put down some names here. All right. All right. Anybody have any suggestions here on whose name should go for the shark here? Anybody? Well, you all know who answering or who not answering. So let's see. Don't worry, I'm not gonna give away your full names. It's just for fun, really. Mr. Doob, you are up here for the shark. Anybody want to volunteer or thought that they were not participating as much in classes as they should? Nicholas, you are up here today. Right. If you think I made a mistake with your name, let me know. You could fight your case. What? Julian? Don't worry, Julian. I won't put your last name. All right. Hey, what? I'll put your last name. I'll leave out your first name. Sorry about that. Anybody else who deserves to be up here? Stephanie, I haven't heard you for the whole day. Right, there's somebody else, someone else. Maya, I haven't heard anything from you today. You go in the little spaceship here. And Cindy, didn't hear Cindy for the whole evening. I know I missed out a few people, but I'll catch you all on the next run. All right, guys, if your name is up there, come on, guys. I know it's for fun. I'm not trying to embarrass you, just for kicks, right? Try to get try your best to participate in class as much as possible. All right. Right. This is all that I could have come up with to encourage participation. All right, so we have one more, right? This thing called heat of solutions, right? So let's review this definition. The heat of solution is the heat change which occurs when 1 mole of solute dissolves in a volume of solvent that further dilution by solvent produces no further heat exchange. So let me just summarize that for you all. First of all, which one is the solute? Is that the solid one or is that the liquid? For example, if you put, sugar dissolves in water, right? Which one is the solute? The sugar or the water? The solid one or the liquid? The solid one, correct. The sugar is the solute, right? So we are concentrating on 1 mole of the thing that is being dissolved. Like the sugar is the one that is being dissolved, and we only care about 1 mole of it and the amount of energy or heat energy produced by the 1 mole of solute, right? Great. Keep that in mind, and you're going to try a question for me, right? Try this question. It's worth $5. A student dissolved 45 grams of potassium nitrate. Now, that means the potassium nitrate is the solute. So my advice to you is to figure out how much moles of potassium nitrate you have in the first place. You have to use this value down here. This is grams, by the way, 101 grams. Right? So good luck. You have 5 minutes. First of all, let's see how much moles of potassium nitrate we have. So let me draw my little cross here. Remember, this here is the molar mass of potassium nitrate. This gives you the mass of 1 mole of potassium nitrate. So we're going to have 2 headings here, moles and mass, right? The mass will be in grams, obviously. According to the molar mass, 1 mole of potassium nitrate weighs 101 grams. Let me just put it here so we don't get lost. We're dealing with the potassium nitrate here. But we only have 45 grams of potassium nitrate. Obviously, that would represent a less amount of moles. So we cross-multiply to figure out how much moles we have. 101 multiplied by x is 101x. 1 by 45 is 45. The 101 is a multiply, throw it across, you get a divide. Let's see how much moles of potassium nitrate we are actually dealing with. 45 divided by 101. And we get in roughly 0.445. But if you gain this, right, 4555, I'm going to round it off to 2 decimal places, so it will be 0.45. So that is what I'm going with. How much people have up to there? Like you were able to figure out how much moles of potassium nitrate you have, and it's always a good idea to go to 2 decimal places. If you go to 3, nothing wrong with that. The examiner will obviously appreciate that more, but you won't get any extra marks. Great. Now, let's try to figure out how much energy was created when this amount of moles was used. So we go back to this formula here. E is equal to M by the specific heat capacity of this by the change in temperature. Now, this is where it gets a little bit tricky, like different textbooks will say different things. The change in temperature, the examiner gave you that upfront, right? The temperature decreased by how much? 10.9. So that is the change in temperature. The specific heat capacity of water is 4.2, right? But what is the mass of the water? And this is where it gets a little tricky. Remember, 160 centimeters cube of water was used. Remember, 1 centimeter cube of water weighs 1 gram. So it's 160 grams of water used. So some textbooks will put 160 here, or some websites. But then it have some other textbooks. Remember, and you mix the 45 grams of the potassium nitrate in the water. So what should be the total mass? If you had 160 grams of water and you add 45, if you add both of them, you will get what? 205. To me, this is the correct way to do it, right? I know some textbooks leave out the original mass that you added to dissolve in the first place. But as far as I know, this is the correct way of doing it, right? Great. So can you tell me how much energy was created with this amount of moles of potassium nitrate? 205 multiplied by 4.2 multiplied by 10.9. I'm getting this. 9384.9 joules. And I think a lot of people just sent me that answer. But you see, this is not the final answer. The heat of solution, right? If they ask you to calculate heat of solution, they are interested in the amount of energy associated with 1 mole of the solute, not 0.45. So you have to do a little cross thing again. Moles and the amount of energy. According to what we just calculated, when we use 0.4 moles of the potassium nitrate, we were only able to generate this amount of energy. But I am concerned with 1 mole of it. Cross multiply and tell me, right? Tell me how much energy is associated with 1 mole of it. I'll do you working up here. Yeah. Across the multiply, you get a divide. Let's see how much we get. I'm getting 20855, and again some decimals, 0.33333. Probably just put 2 joules. That's the answer. I didn't think the revision would have taken this long. All right, guys, I think y'all deserve a small break here. So you all know what to do. You have to choose. You put on your virtual reality goggles because you're living on Mars at the moment, right? Choose 2 letters and a heart. 2 letters and a heart, and hopefully you'll get some extra money. I know some of you are wondering what you have to do with the money that you're winning right now. You'll see in a little while. You better hope you have enough money. right, so let's hope you won plenty money. And let's see what your heart said. For those who chose white, the amount of money you now collected, multiply by 0, which means it's 0. Same thing for pink. And anybody who chose the blue heart or the pink heart, well, you get either a blue card or a red card. Let's see what luck the red and blue cards bring. For those who collected the blue card, you got an extra $10. And for those who got the red card, you collected, oh, sorry, nothing. All right, let's move on. Right. All right. Just to answer one question. All right, so this here is the reactivity series of metals. Remember, all metals, right, are not all metals share the same reactivity. Some metals are just more reactive than other metals. Like you throw some metals with acid, it is start to flame up. That's a very well, a reactive scenario. And sometimes you take a piece of metal and you throw it in water or you throw it in an acid and nothing happens. Well, then it's safe to say that it's not reactive. So this here, like I said, is the metal reactivity series. Potassium is the most reactive. Everything, as you go upwards, it gets more and more and more reactive. And for the CXC syllabus, gold is the least reactive metal. Now, I know carbon and hydrogen are not metals, but they are included in the metal reactivity series. So you could compare carbon and hydrogen with the reactivity of other metals because it helps us to understand other parts of chemistry. Quick question, right? Without looking back in your books. What reacts with calcium, sodium, and potassium? In other words, what reacts with calcium go up? What substance will react with it? Without looking back in your books, then guys, without. No, Fakira. Come on, this is a standard table we did it quite last year. I know we did it quite last year. Nah, you all forgot. It's water, right? Water, plain old room temperature water, that's the water I'm talking about, will react with calcium, sodium, or potassium, okay? The blue line, the iron go up, right? We'll use blue for blue. From iron go up, everybody above that blue line will react with steam. So that means potassium, sodium, and calcium can also react with steam. And it also reacts with water. But things like magnesium, aluminum, zinc, and iron, right, do not react with water. They're just not reactive enough. So it's always the line go upwards. So for the green line, from lead go upwards, it's acids. Acids would react with anybody above that green line. And the copper here, right? From copper go up, that's oxygen. Right? Oops, sorry. Which means that everything below that black line, right? Silver and gold do not react with anything. Well, under normal circumstances, right? That is why silver and gold last so long. That's why the jewelry lasts so long. When you buy something that's pure gold and you put it on your finger, it reacts with nothing in the environment. Hence, it will always stay silver or gold forever, right? Because when things react with other things, they don't remain as their original substances. The point of a reaction is to change it into something else. All right, so this was a table that we had last week. I hope it refreshes your memory, right? Let's move on. Right. Oh, by the way, I just want to point out something, right? Now, it's common to say, right? A lot of people say this. If you take a metal and add it to an acid, right? A metal plus an acid will give the general reaction is, anybody remembers? A metal plus an acid will give you what? A salt and hydrogen. Now, I don't like it when people phrase it like this. This is a general reaction in chemistry, but it makes it sound like this. It makes it sound like if you take any metal in the world and add it to any acid in the world, you are guaranteed to get a salt and hydrogen gas. But that statement is misleading because this statement is only for metals that can react with acid. In other words, from the green line, go up. So lead, tin, iron, all the way up to potassium, fine. Mix it with an acid and you will get a salt and hydrogen. But everybody else below that green line who cannot react with an acid, this general format doesn't hold for them. In fact, if you take copper, silver, or gold and mix it with acid, it will be the world's most boring thing. Nothing will happen. You will just stand there, the beaker will watch at you, and it will just, nothing will happen. So keep that in mind. This statement only holds for the metals that can react with the acid. Which brings us to the next slide, right? And you all know this table here, the solubility of salts. Not all salts are soluble. Some of them just cannot dissolve and they precipitate instead. So, do you think you all could complete these three reactions for me? Magnesium plus HCl, sodium plus H2SO4, and then copper plus HCl. Complete each reaction for me. Actually, let me help you, right? I'm going to do the first one. Magnesium, he is a metal, and he is way above that green line, right? Magnesium can react with an acid, but magnesium is a group 2 metal, right? So you will need 2 Cl's to balance off this. So it will be MgCl2, and of course, you have to get hydrogen, H2. Hydrogen is diatomic. When hydrogen is by himself, right? It's always H2. So I think we have to put what here? A 2 here, right? Now this could be a solid. This could be AQ. All acids are aqueous. This is a gas. What am I putting here, guys? The magnesium chloride. Do I have to put AQ or do I have to put S? In other words, S means solid. It means it's insoluble. And AQ means it's possible to dissolve it. So what am I putting here according to the solubility table? Magnesium chloride, is it soluble or insoluble? And you get marks for that in the exam, right? If you can't remember if you don't remember this table and you put the wrong state symbol, you're going to lose a mark in the exam. Isaiah, you say AQ. Right? This is a chloride. All chlorides, most are soluble. The only insoluble ones are silver and lead, right? So magnesium doesn't fall in the insoluble. So right, you guys are correct. AQ. Right. Sodium plus H2SO4. Sodium is real high up in the metal reactivity series. way above the green line in the previous slide. So what will we get here? You will get, remember, sulfate is 2 minus and each hydrogen is positive 1. So this will be what? You need 2 sodiums because sodium is group 1, Na2SO4 plus H2. We know this is a gas. We know this is AQ. We know this, we need 2 of this, sorry. And this is a solid. What am I putting here? AQ or S? Is sodium sulfate soluble or insoluble? Look at the chart there. And just to answer one question, no, the chart is not given in the exam. You have to memorize it, right? To make it simple, anything with sodium is soluble. Look at here. Sodium, any salt created with sodium is soluble. So it's AQ. Y'all want to do the last one for me quickly? Right. Fakira, you have an answer there. Send the answer for the last one quickly. All right. For everyone who sent an answer, right? Remember, we are mixing it with an acid, right? Remember this? The green line and above is everybody who can react with an acid. Remember we said that? Where's copper? Copper is below that green line. So can copper react with acid? The answer is no. The answer is NR, or no reaction. Or you can write out the words no reaction. Guys, you all fell for that simple trick, even though I showed you it a few minutes ago, sorry. Don't fall for those small tricks in the exams, guys, okay? Not all metals can react with acids, right? So I hope it sticks in your head now, right? Don't feel too bad. If you got it wrong, don't feel bad. The majority of the class got it wrong, right? Jade, you got it correct. So well done. Rates of reaction, right? Now the rate of reaction of things like if you put reactants in a test tube to mix up and to react together, the rate of reaction is how fast it can react. And there are certain things that affect the rate of reaction. Temperature, concentration, and the more concentrated the reactants are, the faster it will react. If you increase the pressure, like the atmospheric pressure, it increases the rate of reaction. The surface area of the reactant. So I think I explained this one here. Which one reacts faster? Let me say we're using potassium, right? We're going to throw potassium in water. Which one would react faster? Big blocks of potassium or powdery potassium? Which one reacts faster? Blocks of potassium or powder form potassium? Right, I'm glad you guys didn't forget. The powder form reacts faster, right? Oops. Write the word here. And I had shown you a brief calculation that the smaller the particles, the larger the surface area. I know that's hard. If you had missed that class, I know that's hard to believe, right? You might find it hard that smaller things have a larger surface area. But when they say surface area, they mean the surface area of everything added up, not the surface area of one dot. The surface area of many dots has a larger surface area than a few cubes, okay? So powder form will always react faster. And of course, if you use a catalyst, one of the main purposes of a catalyst is to encourage the reaction, to make it actually go faster. Right? So everyone grab $5, right? You had nothing to do there. That's me talking, and you get an extra $5. Let's go. One last thing here. Do you all remember this? What topic is this? When you hook up a battery to two conductors, it starts with E. What topic is this in chemistry. It was the second topic we did in September. Electrolysis. Okay, electrolysis. So quickly, the red one, the one that's connected to the positive side of the battery, is he the anode or the cathode? The one that's connected to the positive side of the battery, without looking back in your books. Right, he is the anode. And the one that's connected to the negative side is the cathode. Okay? And over here is the ability of the cations or anions to discharge. Okay? The lower that you go down, the easier it is to discharge. Well, let's refresh your memory, right? Let's take remember the cathode has a positive charge because it's connected to the positive side of the battery, and the anode has a negative charge. Let's take two examples here. Let's take OH and Cl. Let's say that you have Cl minus, one ion inside here, and you have OH minus. Now, both of them are negative. So both of them will be attracted to the anode because opposite charges attract. Both of them, when they rush towards the anode, they dream of being discharged. In other words, they hope that they can lose their negative charge. That's the only reason you rush towards the anode, in the hope that you lose your charge. But the anode can only discharge one of them. It cannot discharge both of them. Who will get discharged under regular circumstances? Who will the anode choose to discharge? Nishan, you sure? Naomi, you sure? Look at the chart here. Look at the chart, the table. This table says as you go downwards, right? Look at it. As you go downwards, it's easier to discharge. OH is lower, so he is easier to discharge. Chlorine is higher. He is harder to discharge under regular circumstances. So the anode doesn't like hard work. He is going to choose who is easier to discharge. He isn't looking to make life hard for himself, right? So the OH will get discharged and the chlorine will get denied. The chlorine will remain as Cl minus, unfortunately. Now, the same thing for the cations. Like if you have calcium 2 plus inside here, and you have copper 2 plus, both of them have a positive charge. So both of them are going to rush towards the cathode in hopes or dreams of losing their positive charge. They want to get discharged. Discharge just means you want to lose your charge. But both of them cannot be discharged. Only one of them can. Who will get discharged here? The easier one. Copper is lower. Calcium is higher. The lower you go, the easier you are to discharge. So the cathode will choose Mr. Copper. Right? Let's move on. Right, participation punishment time. Right? So you all can read the punishment there. Right? So a few people are going to get locked into this little cage here to encourage you all to pay attention, to participate in class. Any volunteers? Anybody volunteers? Anybody think willingly that they're not doing enough in class? Leah, you're up there. Leah, you get thrown into the cage. Makizi, you're there. Mikhail, you are there. Mikhail, you're alive in class. Anybody else want to volunteer? Anybody want to volunteer themselves? Samir, you go. We have a volunteer here, Samir. All right, so Leah, Mackenzie, and Mikhail. All right, try to answer the questions on the next slide. All right, let's try. I know you're tired, but just try your best. Okay. Sorry about that laugh there. All right, past paper time, official past paper time. Give this a read. This is question 1. Like I said, I'm not giving away the year of the past paper as yet. At the end of class, I don't mind telling you. Let me know when you're finished reading. It's a handful to read, but the next slide will summarize all of this. Do you think you all can fill out the table? Now look at what's going on in the experiment. Huh? Basically, you're mixing a metal with an acid. So hydrogen gas is being what? Produced. And the name of the metal is what? Zinc. So what you're doing in this experiment, right? It's 4 things. It's the concentration. Like if you notice, in experiment 2, they changed the concentration of the hydrochloric acid. In all of the other experiments, the concentration of HCl was 0.1. But for experiment 2, they raised the concentration to what? 0.2. And sometimes for the experiment, they use granules. Granules are like big, are like cubes, right? Like gravel. And in experiment 3, they decided to what? Use powder instead of the granules, the powder zinc. And then in experiment 4, they decided to change the temperature of the experiment. You all realize that these things that are being changed for each experiment affect what? Rates of reaction. Do you all think you all can fill out this table for me here? You're just using the gas syringes to determine the volume of hydrogen gas produced. Now, did you all get that? 89, 171, 187, and 46 on average. Most people send those answers, right? McKeezy, it's just the last one, but I think it just made a typo, right? Right. So obviously you're going to get a little, well, you're getting $5 for that there. Right. So you could decide if you get one wrong, just take away $1 or something. All right. So that's easy stuff there. Easy stuff. Define the term rate of reaction without looking back in your textbooks, without looking anywhere. Do you all think you all can give me a definition for rates of reaction in CXC chemistry? And of course, you can see it's only worth 1 mark. And well, today it's also worth $1. I think this is the one that I had given you all some time ago. The rate of chemical reaction is the change in the concentration of reactants or products per unit time, right? So if you have anything close to that, I don't expect you to have the exact wording, but refrain from saying it's how fast a reaction occurs. I'm 100% sure you'll get 0 marks for that in the exam, right? Right. So let's move on. Right. So good luck with part C. I'm going to give you I'll give you 5 minutes, a full 5 minutes to do this one. Right. So part 1 is this equation, right? If you notice, metal plus an acid give us a salt and hydrogen, and zinc chloride is soluble. So you have to put the AQ. But part 2 now. What is the oxidizing agent? First of all, when something is oxidized, does the charge get larger or get smaller? When something is oxidized, I'm repeating the question. When something is oxidized, does the charge get larger or does the charge get smaller? Right, it gets larger because remember the opposite of oxidation is reduction. Now the name reduction makes sense. Reduction resembles the word reduce. So if something gets reduced, the charge gets smaller. But oxidation is the opposite. So let's look at the charges. Let's reason out the charges. Zinc is by himself. Well, whenever you have an element by himself and he's not attached or bonded to anything, his charge will be 0. So right now, the charge on this zinc is 0. The charge, well, this is hydrogen bonded to what? Chlorine. We know that the charge here is +1 and chlorine is -1. That's pretty easy. After the reaction, right? The zinc will have a charge of +2, and chlorine still has a charge of -1, but it have 2 chlorines, right? So, but the oxidation number will be -1. And now the hydrogen is by himself. So the charge on the hydrogen is 0 because the hydrogen is not bonded to a different element. So who got oxidized? Who charge got larger? I would say the zinc got larger. Look at it. The zinc went from 0 to +2. So the zinc was oxidized. Now, the zinc didn't oxidize himself. An item cannot oxidize himself. Something had to push it to be oxidized. And that would be the oxidizing agent. So who's the only other item over here? The HCl. The HCl is the oxidizing agent. Right? So for those who said HCl, you are correct, right? The oxidizing agent causes the other item to be oxidized, okay? By the way, who was reduced? Who was reduced? Let's just ask that question. Who was reduced? Who charge got smaller? Right, so people are getting the crowd. The hydrogen, right? Any hydrogen started off at +1, and after he went to 0, isn't 0 smaller than 1? So who is the reducing agent? If hydrogen got reduced, who caused it to be reduced? It will be the zinc. The zinc is the reducing agent, okay? It's always the other person, the other substance. Right, so part 3 now, guys. You have to do some calculations here for me. So I need all the space I can. So I will start the working up here for part 3. So let's see how much moles of zinc we have. Moles and mass. So down here they told us 1 mole of zinc weighs 65 grams, right? That's what this statement means, right? I find they should have put the G here, but it didn't. So, and we only have how much? 1 gram of zinc. So how much moles do we have? We just cross multiply, right? 65 by x is 65x. 1 by 1 is 1. So throw across the multiply, you get a divide. So we have 1 over 65. I don't think that fraction is going to look that decimal is going to look too good. But you're going to get 0.015 or something like that, right? I know some of y'all might go to 0.02 instead of 0.015, but I'm going to go with the 0.015. Now, here's what they said, right? 1 mole, we need let's look at the ratio. It have a big 1 in front here. There's no 1 rooted. And in front of the hydrogen, there's a 1. So the ratio is still 1 to 1. When you're considering ratios, it's the number in front of the item. So that means the ratio of zinc to hydrogen is the same. So if I have 0.015 moles of zinc, that means also 0.015 moles of hydrogen was produced. So let's go here and do the hydrogen calculations now. Moles and volume. They said 1 mole of gas occupies 24 dm cubed. So 1 mole of any gas occupies 24 dm cubed. That's the volume measurement. We have how much moles? 0.015. So how much volume would that occupy? Well, we have to cross multiply. 1 by x is x. And then 24 by this is 24 by 0.015 is 0.36 dm cubed. I know some of you all rounded off different here. So you got 0.37 or a little less. But anything about 0.3, anything close to 6 will do. Right? So the money goes $1 for this one, $2 for the second part. That was to figure out which one was the oxidizing agent, and $3.3 for the one below, bringing the total to $6. All right. So I believe this was the end of question 1, right? We didn't get a chance to use the money right now. We're only on question 1 of the past paper, right? I know it took us a long time to reach here because we did so much revision, but I believe the revision was worth it. I'm still not going to give away the year of the past paper. Next week, when we finish the past paper, I will give you the year. That's to prevent anyone from, Googling the answers and just having it prepared for next week. So guys, I know we were supposed to go to 7:15, but I could sense the tiredness on everyone here. So every week I'll go an extra 20 minutes until I make up all the times for everyone. So guys, I'm not going to hold you back too much. Have a good night, and I'll see you all next week, and I'll see some of you on Sunday for physics.